All right, so today we are going to start chapter 5, which is on the subject of energy. So there's like gunk on the screen here. Let's see if I can get that. Okay. Sorry, there's a question in the chat. Will we be allowed a cheat sheet for the test? Like, yes, you'll be allowed your usual 3x5-inch index card, handwritten notes, no example problems. Yeah. Any other questions about the test? All right. So in chapter 5, we are going to introduce the concept of energy. This is a word that is very common in our everyday usage. And we will see in physics, it has a very precise meaning. And we will sort of be on a journey in chapter 5 to discover this concept of energy, what it is and why it is a useful thing to talk about. One of the nice things about this chapter is if you hated vectors in the previous chapter, adding vectors and things like that, here we can analyze a lot of the problems that we looked at before using energy methods, where you don't sort of use vectors, but you think more conceptually in terms of energy, and you can actually solve a lot of the problems that we solved before using energy methods. You can't solve all of them, but a lot of them you can do by thinking about energy. Okay, so as I said, energy is one of the most important concepts in physics. We use it in everyday contexts, but it has a precise meaning in our study of classical mechanics. There are different forms of energy. So here are just some names. We will introduce the idea of kinetic energy, which is the energy associated with the motion of an object. There's things like gravitational energy, there's chemical energy, electromagnetic energy, nuclear energy, thermal energy. There's different types of energy that we will encounter. We will talk about kinetic energy. We will also talk about gravitational potential energy a little bit later on. Do any of you recognize what this device is? It used to be a thing called a TV. Yeah, okay. Say it again? Cathode ray tube television, that's right. I used to have one of these until 2014. And then when I had to move down here to Georgia, I got rid of it. That's right. It's like a distant memory for you. Yeah, it's like VHS tapes, that's right.
Those were so much fun.
Yeah. Just for your historical knowledge, these things used to be on top of a stand, and then below over here, you would have something called a video recorder, and in that you would put like little VHS tapes. So Google it, look it up.
I remember I would rewind a lot of
That's right.
tapes. They were so much fun. I miss those days.
That's right. Yeah, simpler times. The attendance code, anyone remember the attendance code? 0674. I should make that like a top hat question 20 minutes into the class. What is the attendance code? And everybody's on board. Anyway, we have more fancy looking TVs now. But the basic idea here is that the way this device and the way many devices work is they basically convert one form of energy into another. So there's some electricity coming in, so there's some electrical energy being sent into this television set from a power station. And that energy, a bunch of magic happens here in the box, but in the end, that electrical energy that goes in is converted into different forms of energy like light, sound, and heat. And so this, again, will be an important concept of how we convert one form of energy into another. So again, as I said, energy can be transformed from one form into another. The total amount of energy in the universe never changes, as far as we know. Although that's not quite true if you go into cosmology, but anyway, sidetrack. And this idea of energy can be used in place of Newton's laws to solve certain types of problems more simply. And it'll provide a link between force and energy. So we will kind of unpack all of these concepts in this class. Now, as I said, we will go through a journey and we will discover the idea of energy and why it's useful later on. And we're going to start off by introducing this quantity called work. And at the moment, it's just sort of a arbitrary definition. It's not clear why I'm talking about this, but we will see that it will be a useful thing to think about. By the way, did that person get the attendance code? Did we actually say what the attendance code was?
Yeah.
Oh, okay, we did say it. What was it? 0674. Okay, so this idea of work here, it's a word, it's a definition, and here's how I'm going to define it. And again, like I said, at the moment, this definition is not motivated, but we will see that it will be a useful thing to think about later on. So let's imagine that there's some box here on this floor, and maybe someone is pulling on this box with a rope or something. They're exerting this force F. And as they're exerting this force F, the box slides on the floor and comes to this location over here. Okay. And then what this picture is showing you here is that this force F, if it is applied at an angle of theta relative to the ground, you can decompose it into its components. This F can be, F cosine theta along the x direction. And then I guess this would be like a F sine theta along the y direction, right? Just our usual decomposition of vectors. So when this happens, I can go ahead and declare that in the journey where the box went from here to here, this force F has done some amount of work, and we will define that work to be F d cosine theta. So F here is the magnitude of the force. D here is the magnitude of the displacement, the distance covered on the ground here. And theta is the angle between the force vector and the displacement vector. So that's just the definition. So if someone is pulling on this box with this force F and it slides over here and someone asks me how much work was done by that force, I will take the magnitude of the force, the magnitude of the displacement, and then look at the angle between the force and the displacement, take its cosine, multiply them all together, and that'll be the definition of the work done by that force. Any questions on that? They've kind of suggestively put this F cosine theta here in brackets to kind of indicate that in some sense, you can think of this in another way, that the work done by this force F is just the product of the component of the force along the displacement direction times the magnitude of the displacement. So this F cosine theta here is just this component of the force that is in the same direction as the displacement. So that's another way of thinking about it, but if you prefer, you can just think of it as F d cosine theta. And so again, here, d here is the magnitude of this displacement vector. Notice that, as I say on the next slide here, work is a scalar quantity. This is a scalar number. You just take the magnitude of the force, the magnitude of the displacement, cosine of the angle between them. It'll give you some number. There's no direction associated with it. We don't say how much work you did going north or east. It's just a number. Also notice that this number, it can be positive, negative, or zero. So the magnitude of the force here is always a positive number because it's just the magnitude. The magnitude of the displacement is also a positive number because it's also just the magnitude. But this cosine of theta can be positive or negative. Right? So for example, if this theta here, if it's 20 degrees, cosine of 20 is a positive number. But it could be that this angle is like 120 degrees or something. Maybe there's a force that's being applied in this direction, like a new force, let's call it F prime or something. Then it might make this bigger angle alpha. Then the work done by this force F prime will be its magnitude F prime times d times cosine of alpha. So in this case, again, the magnitude of the force F prime is positive. The displacement is still D, but then the angle between them is between 90 and 180. And so the cosine of that angle is negative. Any questions on that?
Sorry, you said work can be positive, negative, or zero,
Right. Or positive, zero, or negative. Are you?
but then would that make it not a scalar? Because would that be giving a direction?
That's a good question. Yeah. So scalar quantities can have negative values even without direction. So for example, something would have a temperature of minus 20 degrees Celsius, right? So it's true that in when we're talking about like components of vectors or one-dimensional vector, then it's positive. If it's positive, it means it's pointing in the positive x. If it's negative, it means it's pointing in the negative x. But for scalars, there's no direction associated with them, but they could still have negative values. Any questions on that? We can also define something called the network done on an object. And this is when you take all of the forces acting on the object, compute the work done by each one of those forces, add them all up, that is a net force. Right, so for example, in this particular picture here, let me go ahead and erase this. If I were to draw a free body diagram for this box, let's do that here. Let's say this is my positive x and positive y. If I were to draw a free body diagram for that box, what are the forces? There might be a force of gravity down, mg. There can be a normal force.
Zero. The force due to gravity is also zero, but the force of friction is -1.
Well, the forces are not zero. The work
Oh,
they're
the
doing
work.
is zero, right?
The work done on it.
Right.
Thank you.
The work done on the box by the force that you're talking about. So the normal force is not zero, gravity force is not zero, frictional force is not zero. They're each doing some work on the box. The normal force and the gravitational force are doing zero work on the box. The force of friction is doing negative work on the box. And this force F will end up doing positive work on the box because this angle will have a cosine that is positive. So that kind of is illustrated here. It's not a top hat question, but you can see here, there's zero work done in this situation where the force is perpendicular to the displacement. In this case, it's negative because there's a 180-degree angle between them. In this case, it's positive. The angle between them is zero. The force and the displacement are in the same direction. Cosine of zero is +1. And in this case, maybe this angle is like 120 degrees or something. This force will be doing negative work as the box moves to the right. Any questions on that? So there's all these multiple forces acting on the box. The box is going to have an acceleration and it's going to move depending on who wins, right? What the net force is. But in that process, each force in there will be doing its own work, which may be positive, negative, or zero. All right, so here's some top hat questions. So let's see if we can answer this question here. So there's someone just carrying a bucket and they're kind of walking, holding on to it the way they have, and they're walking forward. What is the work done by the force of gravity, in this case, on the bucket? So let me switch here. So calculate the work done in this case. By the force of gravity. All right, 5 seconds. So we got. All right, and most of you got it. It is indeed 0. And just very quickly, the reason it's 0 is because the work done by the force of gravity in this case will be its magnitude mg times the magnitude of this displacement to the right times cosine of 90 degrees, because this angle between the displacement and the force is 90 degrees. And cosine of 90 is 0. Because cosine of 90 is 0. On that. Let's look at this example here. Yeah. Okay, so here's another, they're trying real hard to connect with you. So they're saying there's a student over there that's lifting a box. And is the work done by this lifting force as the box is lifted up positive, negative, or 0? So let's see here. Oh, so you wanted to see the picture? Oh, whoops. Oh, I guess the picture is over here. So yeah, there's the picture. Kids lifting the box up. What is the work done by the force of gravity? Sorry, by the force that the student is applying upward as the box moves upward. All right, 5 seconds. All right, so most of you got it. It is indeed positive, and that's because the box is going upward, so its displacement vector is up. The force being applied is also up, so the angle between them is 0 degrees. So you get FD cosine of 0. Cosine of 0 is 1, so you just get F times D, which is a positive number, since F and D are both magnitudes. Let's see, is there another? Yeah, so here's another question, which is now in the same problem, as the student is lifting the box up, what is the work done by the force of gravity? Is it positive, negative, or 0? The force work done by force of gravity. So here's that question. What is the work done by the force of gravity as the box is being lifted up? All right, 5 seconds. And indeed, most of you got it. It is negative because the box is moving upwards, displacement vector is pointing up, force of gravity is pointing down. So the angle between them is 180. Cosine of 180 is -1. Okay.
Second one, I didn't get it.
The second what?
Second question. The one about,
This one?
no,
This one. The work done by this force F will be positive because the displacement, the box is moving upwards. So the displacement vector is up. The lifting force is also up. So the angle between this vector and this vector is 0 degrees because they're both pointing in the same direction. So therefore, the work done by the force of F here will be F d cosine of 0 degrees. And this is just +1. And so therefore, it is positive. Any other questions? All right. So let's do a example where we kind of do a calculation where we calculate the net work done on so let's see here. So we have this situation where there's this person that is pulling on this sled, which has some fish on top of it. And the question is, what as the sled moves to the right, so they're telling us that this sled here, along with the stuff on it, altogether weighs 50 kilograms. They tell us that this person exerts this force F that has a magnitude of 1.2 times 10 to the 2 newtons, or about 120 newtons, is the force in this rope, this force of tension in this rope. And they also tell us that the coefficient of kinetic friction between the sled and the snow here is 0.2. So that will give us a reminder of how to use the force of friction from chapter 4. They tell us that this angle here is theta degrees. And then they tell us that he pulls the sled for a distance of 5 meters to the right. And in that journey, when all these different forces are acting on that sled as it moves 5 meters to the right, what is the net work done on this sled? Any questions on that? So that's what we're going to calculate, is what is the net work done in this journey. And again, just to kind of remind you, we've arbitrarily introduced this notion of work, but we will see that it is a useful concept later on, and will lead us eventually to the idea of energy. And right now, we're just learning the techniques on how to calculate this thing called work. So the first thing I will do is remember that the net work done is the work done by all of the forces acting on the object added up together. So that means the first thing I want to do is I want to draw a free body diagram for this sled so that I can identify all the forces that are acting on it. Right? So here's the free body diagram. Again, let me choose my positive x to the right, my positive y upwards. Well, we know that there is the force of gravity down, mg. We know that there will be a normal force upwards from the ground. We know that there is this force F at an angle of theta. So let me kind of do that. And we know that there is a force of friction, the force of kinetic friction. And if you recall, the force of kinetic friction is the coefficient of kinetic friction times the normal force from chapter 4. So those are all the forces acting on this object. And so now I can come down here and I can say that the net work done is equal to the work done on this object, whoops, by the force F of the person pulling on it, plus the work done by the force of kinetic friction, plus the work done by the force of gravity, plus the work done by the normal force. And here we are also told, by the way, that the distance d is 5 meters, right? The sled has traveled a distance of 5 meters. So we'll use that piece of information. So let's go through this calculation here real quick. What will be the work done by the force of force F? Well, that'll be F times the d times the cosine of theta, literally this theta right here. It's going to be F times d times the angle between them, cosine of the angle between them, FD cosine theta. Right, and we're given all this information. Maybe I should collect that over here. We are told that d here is 5 meters. We are told that theta here is 30 degrees. We are told that the mass of the sled plus salmon is 50 kilograms. We are told that the magnitude of the force F is 120 newtons. And we are told that the coefficient of kinetic friction is 0.200. So that's the information that's given to us. So for this force, work done by the force F, we know F, it's 120 newtons, D is 5 meters, theta is 30 degrees. So we know how to get that number. Then let's go to the force of friction. Well, what is that? That's going to be the force of kinetic friction times D times the cosine. What do I put for the angle there, anyone? What is the angle between the force? Yeah, go ahead. 180, right? The force, the angle between the force of friction and the force of and the vector of displacement. Displacement is going to the right. The sled is moving to the right. The force of friction is in exactly the opposite direction. So the angle between the displacement vector and the force of friction is 180. So here I will come in with cosine of 180 degrees. Is that clear to everyone? What about gravity? That'll be mg times d times cosine 90. That's right. So mg is down, displacement is to the right, so the angle between them is 90 degrees. And then the same thing for the normal force. It'll be the normal force times d times cosine, again, of 90 degrees, because the normal force is upwards, the displacement is to the right, the angle between them is 90. So cosine of 90 is 0, so I can just go ahead immediately and set these two to 0. The work done by gravity and the normal force is 0. In fact, the normal force always does 0 work, because the normal force, if something is sliding on a surface, by definition, the normal force is always perpendicular to the surface. So it's always going to be applying a force perpendicular to the motion, and therefore it'll always be 0. The force of friction will always do negative work, because it's always going to be in the direction that is opposite the motion. With the other forces, you have to kind of think about what is happening. So then we get here that this is equal to 120 newtons times 5 meters times cosine of 30 degrees plus, oh, actually, I should, before that, before putting in the numbers, I need to do a bit more work, which is, this is FD cosine theta. And then the force of friction kinetic friction here, remember, is given by the coefficient of kinetic friction times the normal force from chapter 4. And then you have here cosine of 180 degrees. And then the other two terms are 0. So all I've done is taken the force of kinetic friction here and replaced it with the coefficient of kinetic friction times the normal force. And cosine of 180 is -1, so this is the same as FD cosine of theta minus mu k times n. Any questions on that? But now notice that I know how to calculate. This term because I know f, I know d, and I know theta. I know all those numbers. In this second term, I know that mu sub k is 0.2, but I don't know the normal force. The normal force is not given to me. And so we need to calculate what is this normal force in order for me to be able to get what is the full work done. Say again. How are you getting 490? So yeah, there's a bit of a subtlety here. That's a good. The subtlety here is that. So the logic you may have used is that the sum of the forces along the y direction must be 0, because the sled is only moving along the ground, it's not going up, so there's no acceleration up or down. And so therefore, the sum of the forces along the y-axis must add up to 0. And so you might say, therefore, the normal force must be equal to the force of gravity. But notice that there's this force F here, and it has a vertical component. Right? And so what we want to do is we want to decompose that into its components. And we can now do that and say that now I will have here to the left, there is the force of kinetic friction. Down here will be mg. To the right will be F cosine theta. And then upwards will be the normal force and F sine theta, right? Because I'm taking this force here and I'm writing it as something along the x-axis, F cosine theta, plus something along the y-axis, which is F sine theta. So I'm resolving that thing into its components. Any questions on that? So now to find the normal force, N, use Newton's second law. In the y direction, which is that F net in the y direction, which is mass times acceleration in the y direction, will be 0 since there is no acceleration in the y direction. And what is the net force now? I can now look at this picture here and look at my forces along the y-axis, and I will get N plus F sine theta minus mg is equal to 0. And therefore, the normal force is equal to mg minus F sine theta. Questions on that? And so let me say that up here, this is your W net. Let me call this equation 1. Let me call this equation 2. And so now what I can do is use 2 in 1 to get now the net work. So now the net work is FD cosine theta minus mu sub k times this normal force, which is mg minus F sine theta. Notice that the normal force is less than mg, and that's because the person is pulling up on the sled, so the ground has to do less, apply less of a force to keep it from falling to the center of the earth. And now you can plug in numbers, and if I do that, you should get, yeah, if you do that, you will get 0.9 times 10 to the 2 joules. So I will now say here, plug in numbers, and you will get W net. You can check this as, if you're OCD about it, you should be 0.9 times 10 to the 2 joules. 0.90 times 10 to the 2 joules. That is the net work done on the object, right? And you're just plugging in numbers from here. So you just take all these numbers here and plug it in. You should get that answer. Any questions on that? All right, I think I'm out of time, so let me go ahead and stop right there.